Learning Outcome 9-7. Sketch the approximate magnitude and phase of the Fourier transform based on pole zero locations. You learned in Circuits 2 how to plot poles and zeros in the complex plane. We're going to build on this to get an estimate of the magnitude of the Fourier transform based on the locations of these poles and zeros. You learned earlier this chapter that along the imaginary axes is where our Laplace transform becomes our Fourier transform. Small values of omega are down here on the axes. Large values of omega are up here on the axes. The magnitude of our Fourier transform is going to be the product of the distances from any value of omega to the zeros divided by the distances from any value of omega to each of the poles. So if we consider values of omega, starting with a small value, we have a certain distance to that pole. As that value of omega is increased, that distance is getting smaller, and it will continue to decrease until we are directly across from that pole. That is where we will have a minimum distance to that pole, beyond which the distance will increase again. Because the distances to the poles are in the denominator, we want to convert this concept of distance to poles into a 1 over distance to poles graph. Where we have a large distance, 1 over that will be small. Where we have a small value, 1 over that will be large. Therefore, we can determine that a maximum in our Fourier transform will occur where that distance is smallest, which is at the omega value across from our pole. Because we have two poles, we will have two maxima, one across from the top pole, one across from the lower pole. Next, ask yourself, where will there be minima? In a similar fashion, we're looking at distances to zeros, and those distances along this axis are going to be minimum when we're closest to this zero. We do not have a 1 divided by, so wherever we're closest to a 0, we will have a minimum. The magnitude of our Fourier transform as omega approaches infinity is the next thing we want to find out. It will become a salient feature in a sketch of this graph. Omega is positive infinity when we're way up here, and we'll have distances to our zeros divided by distances to each of our poles. We have 1 0, so we have an infinity, and 2 poles, so we have an infinity squared, which in the limit is 0. That means that our Fourier transform magnitude will approach 0 as omega goes to positive infinity. What happens to our magnitude as omega approaches negative infinity? We start off at negative infinity down here, distance to our zeros, distance to our poles. Again, we have an infinity divided by infinity squared, which means that as we go to negative infinity, we also approach 0. This should make some sense, being as we have a real system and we know that the magnitude of our Fourier transform will be even. So we're seeing the same effect on positive omega as we see in negative omega. The next question to ask yourself is, does this Fourier transform ever have a magnitude that's not finite? This will occur if our denominator goes to 0, and that would occur if one of our poles was on the imaginary axis. In such a case, instead of drawing a finite maximum sketch, we would draw a pair of asymptotes. But because this example does not have any poles on the imaginary axes, we do not need that. But that's how it would work for other problems where the poles are on the imaginary axes. The last question to ask yourself is, does it ever have a magnitude exactly 0? Not just a minimum, but a minimum that has a value of 0. This would be the case if our distance to our zeros, our numerator, were to be 0. And that would be if our 0 were on the imaginary axes. In this example, our 0 is not on the imaginary axes. So this minimum, make sure you do not draw it touching the 0 value. If this were on the imaginary axes, you need to make sure to draw this that it will be touching the 0 value and label it as such. Now we've answered these 6 questions, you can take all these pieces and draw a sketch of what the Fourier transform would look like.